From now on, this video will get into specifics which go a little bit beyond what you need to know about correlational studies, for class. So you don't really need to watch the rest of this video, but it's for curiosity's sake. You're not going to be tested on the rest of this. But if you're interested in finding out more about correlational studies, I'm going to teach you a little bit more about it. Now, the first thing you want to talk about when you talk about correlations is you want to describe the strength of this relationship, the direction of the relationship that exists, and the significance of the relationship. To explain this better, the best thing to do is to look at graphs from correlations. The first type of relationship that could exist between two variables, say for example smoking and cancer, would be a positive correlation. And what a positive correlation means is if you put a graph of the independent variables, so in this case for example smoking would be the independent variable because it's what you're changing, and then the dependent variable would be cancer, which is the outcome. So you're trying to establish cause and effect between those two things, but you can't because it's not truly an experiment. But if you see a pattern in the data like this, you smoke a little bit, you don't have that much cancer, and then the more you smoke, the more the cancer also comes. But if you see a pattern like that, then that means there's going to be what we call a positive correlation, that when one increases, the other one increases as well. You can see this positive slope in the data, And when you calculate the statistics of this, this is what you see. But if you were looking at exercise in cancer, the relationship will probably be the opposite. It will be what we call a negative correlation, because the more you exercise, so that means the more you exercise, the less cancer you're going to have. So when you go this way, the cancer will go down. So you see, as you increase the exercise, the cancer goes down. So the pattern will be different in that case. So the first one is what we call a direct relationship, and the second one is what we call an inverse relationship. Where you could say in the first one, if A increases, then B also increases. But on the second one, you would say if A increases, then B decreases. So they're opposite from each other. One has a positive slope, the other one has a negative slope. You see here, you have a negative slope here, and all the other ones are positive. So what those numbers are telling you is the direction of the relationship that exists between the two variables. Now, sometimes the data is so all over the place that there is no relationship. Something like this, for example, the points, if you do the scatter plot, which shows the distribution of the data, if you do that, you will see that there's absolutely no pattern. There's no line that best fits this data to establish a pattern. So this means there's basically no correlation. Like these numbers over here that you see, there's very low numbers, very close to zero. I can tell you that's barely any correlation. The data is really scattered. The closer the numbers are to 1, the more like an actual line the data looks. A correlation where all the data, all the points are on the line would indicate a correlation of 1, But a correlation near 0 means there's no relationship, and then the numbers are far from the line. So this is now going about the second thing, the strength of the correlation. A strong correlation means that it's very likely that this relationship is true every time. And so the data will really closely be fitted by that line. All the numbers will be close to the line. But a correlation which is weaker will see numbers which are further from the line. Something like this. You're still going to have a pattern, perhaps, but not as closely as you had before. So that's the difference between a strong correlation and a weak correlation. So, for example, if you look here at the violence correlations that we're seeing here, preference for violent TV in the 3rd grade was correlated with aggression in the 3rd grade by 0.21%. And aggression in the third grade was correlated with aggression in the 13th grade by even a higher correlation. What that means is that there's a stronger correlation between the aggression staying the same across the years than there is between TV and the 3rd grade aggression. And also notice that by the time you are in the 13th grade, watching the violent TV doesn't really correlate with aggression. In fact, it's the opposite. You're aggressive even if you don't watch the violent TV by the time you're in that grade. Which means there's very little correlation here as well, because if there's a strong correlation here and no correlation here, usually that means there's no correlation there. So you see how you're establishing correlations between all these variables. This is what we call a multifactorial design, and where you're trying to see a relationship that exists between two variables across time. So this is a very interesting kind of correlational study where they measure the same thing twice and compare correlations between all the variables to see the relationships that existed. But notice interesting though that the preference for violent TV in the 3rd grade did correlate with aggression in the 13th grade. And it's a pretty strong correlation in psychology, a 1/3 chance that this is going to make a difference. And so in this case we say, no, that's very interesting. But in addition to these strength business, there's also the significance business. And by that I mean, does this correlation, strong or weak, whatever it is it likely that this correlation happened by chance, or did it actually happen because you're truly seeing a pattern that exists in the real world? So in other words, when you did the study, did you accidentally fall upon a correlation, or did this correlation really did exist? So we do statistics to figure out that. So we get the significance of the correlation, which is represented by, the statistical value of that correlation. And so when you describe your correlation, you want to talk about the direction that exists, and then you can look at the sign or the slope of the line to tell if it's a positive correlation, where one increases, the other one increases as well, or a direct relationship, or a negative correlation when one increases and the other one decreases, or an indirect relationship. Or when there's no relationship at all and the data is scattered all over the place. Now you also have to talk about the strength of the correlation, and the closer the numbers to 1, the stronger the correlation is, whether it's -1 or +1. The closer the number is to 0, the less relationship exists, the weaker the correlation is. And the more scattered the numbers are in the plot. And then there's also the significance, which is trying to measure whether or not this correlation that you found could have happened by chance alone. Okay? So this is a good example of how you describe data in correlational studies, but there's also other problems with this. Even if you have a great correlation and all of that, there's a problem with correlational studies. That's the problem of directionality. You can't really imply when you find a correlation that A leads to B. It could also be the other way around. It could be that B leads to A. For example, look at this survey, that is comparing no preference for watching TV and aggression in the 3rd grade. So you could say, oh, okay, it seems to be a relationship between wanting to watch TV and having the aggression in the 3rd grade. And there's a 0.21 relationship. But then you might ask yourself, well, are they aggressive because they watch the show, or do they watch the show because they're aggressive? Do you see the difference there? There's a problem with directionality. You can't really say which one causes the other, in which direction the relationship goes. So it's really hard to use correlational data. Let's look for here, for example. Then this also means that there's going to be a problem of causation. You can't imply that one thing causes the other. Especially there's several reasons for that. First, because there might be more than one thing changing at a time. So because you never control things, you never made sure that preference for the violence TV was the only thing changing. You never looked at the other factors. You never did a control experiment. So you didn't have constants. So because there's more than one thing changing, because you didn't have control groups, you didn't really have control over this analysis. You're just comparing a relationship that you observe. Look at the cancer example we're talking about with the cigarettes. You didn't control whether they smoked or didn't, and you also didn't control all the other variables, the exercise, the diet that they have, the rest that they have, the exposure to sunlight, the exposure to mutagens, everything else about that could cause cancer. You didn't control for that. So how could you say that smoking causes cancer if you didn't control all the constants and you didn't even have a control group? There might be what we call confounding variables, other variables which are there and being the real cause, then that's why you can't make sure that the smoke causes cancer or not. So because of other variables and because of the directionality, it becomes harder for you to say that the correlations are causing causation. So because of that, people have tried to come up with research methods to improve the value of correlational studies. And there are some things that you can do to solve this problem. The first one is called partial correlations. So let's say, for example, you're trying to figure out the relationship that exists between A and B. And let's say A is smoking and B is cancer. So you see that you want to find out if there's a directional relationship between A and B here. But then you also have exercise, you have diet, you have exposure to other chemicals. You have a lot of other things that could possibly affect B as well. Right? So you have other things which could lead to the same outcome. So you can't be sure, when you see that there is a relationship between A and B, you can't be sure that this relationship exists because of A is leading to B, or because there are other variables, it's what is actually causing that. So the way to solve this problem is to quantify the correlations that exist between all these variables. So like, How much is A related to B? How much is C related to B? How much is D related to B? How much is C related to A? How much is C related to D? How much is C related to E? And when you calculate all these correlations, you do a statistical thing where by looking at how they're all related to each other, there's math that you can do, and it goes beyond the scope of what I want to teach you, but there's math that you can do to determine how much of the effect of A and B is attributed to the effect of C and A, and therefore how much is C contributing to this thing that you're seeing. So in other words, you do partial correlations that exist between the other possible variables and A to figure out how much of the effect of A and B is because of A by itself. And that's what we call partial correlations. It's a way to control a little bit more the result that you see from a correlational study. So for example, if I'm doing the aggression and the violence, I can control for the family environment. I can control for genetics. I can control for video games they play, for the food that they eat. And then I can calculate how much of the effect of the preference for the TV show is actually causing the aggressive behavior when you consider all the other things and the relationships of those other things have. And this is what we called, you do this with something that we called multivariate correlations as well. You know, where you're looking at many relationships and doing math and statistics to discover how much of that variable can be attributed to what you actually want to experience. Now, another thing that you can do to make things better is to avoid representation errors. You know, make sure the group or the model that you study truly represents the whole. So in other words, create good samples when you getting this group to analyze it. Because if the sample is something peculiar about them, then there's going to be a problem. We're going to talk about sampling in the next video. But what I'm talking about here, if you have a good representation and you have your sampling techniques are good, you're also going to reduce the amount of external variables or confounding variables which are going to hurt this. And you can also do what we call a cross-legged design. This is what you see over here. A cross-legged design is what you see on the top left. When you do something like this, it's easier for you to establish causation because you're measuring the thing across time, and then you can see if it truly makes a difference. In other words, if I measure smoking now and smoking later and the cancer, I can do a better way to look at causation to see if there is a pattern that perceives through time. So cross-legged designs involve measuring the people across different times periods so that you can be a little closer to implying causation. But when you do a correlational study, you can never truly say that A causes B because you're not controlling. Even when you do multivariate analysis, even when you do partial correlations, even when you do cross-legged design, you're not truly controlling. You're just mathematically trying to assess the value of other things. And so it's not exactly a control experiment. And so that's why in the next video we're going to talk about the value of empirical studies or controlled experiments. See you guys then.